Hi everyone, I'm Abdulaziz Salah Alabbad. I'm a master student at Prince Muhammad bin Fahd University. Welcome to our presentation, to our research. My title is Heat Transfer Enhancement of Plate Heat Exchanger, working with water-based nanofluid. I'm with Dr. Esam Jassim and Dr. Syam Syndar. Our thesis will be as a thermodynamics line. Also, it will be research now. First of all, we will start with our outline. Firstly, the introduction, then the thermophysical properties of nanofluid, heat transfer and plate heat exchanger. Then we will move to the result and discussion. Finally, the conclusion. As you see here, the nanofluids. Nanofluid, it's a fluid containing nanometer metallic particles called nanoparticles. Thermal properties of nanofluid will be the density, thermal conductivity, viscosity, specific heat. And also it will be the thermal properties of nanofluid are much higher than the base fluid. As we see here in the figure, this is the nanoparticles, for example, the aluminum oxide with base fluid. In our work, we already choose the water, but it could be another base fluid, for example, oil or glycol or whatever. Then we mix with the nanoparticles and the base fluid that we already created, the nanofluid aluminum oxide water. So the nanofluid play a distinguished role in enhancing the heat transfer mechanism. That's all. We will move now to the next point. Next point will be the thermophysical properties of nanofluid. There are a lot of thermophysical properties. For example, the dynamic viscosity, heat capacity, electrical conductivity, density, viscosity, specific heat. But in our work, we already choose the four properties: density, thermal conductivity, viscosity, and specific heat. There are main factors that cause change in thermophysical properties. Are the shape, size of nanoparticles in addition to concentration of nanoparticles and purity level. All these factors are play a cause in the change in thermophysical properties. When we want to calculate the thermal conductivity, we have to choose this kind of formula. When we want to calculate the volume concentration, we have to choose this formula. When we want to calculate this viscosity, we can choose this formula. When you want to calculate the specific heat, we can choose this formula. Finally, about the density, we can choose this formula to calculate the density. We will move now to the heat transfer. Heat transfer in plate heat exchanger. This formula, it can be calculated by these common formula, which will be about the hot fluid and also to the cold fluid as a nanofluid. To take into account the thermophysical properties of water, hot fluid, and nanofluid, it will be calculated from these formula. At the fluid of mean temperature, we can choose these two formula to calculate the temperature of hot fluid and temperature to the nanofluid. After that, we can calculate the average heat transfer in the hot fluid. If the hot fluid, also we can choose the log mean temperature difference for counterflow. We can choose this formula. After that, we can move to the log mean temperature difference and the average heat rate to calculate the overall of heat transfer coefficient. After we obtained the coefficient for non-fluid, we can use this value to determine the following: the Nusselt number, the Brandon number, the Reynolds number, and finally the mass velocity here. All of these value we can determine by this formula. Also, this one, after we already took the velocity of the value in the previous equation, we can calculate all the value from here, this information. Our objective in this file. The objective of this study to evaluate the effects of applying nanofluid in a plate heat exchanger. We used in this study for distinct types for nanofluid: aluminum oxide, copper oxide, iron oxide, and titanium dioxide. To conduct several tests, our main objective are three objectives. Firstly, to study the effect of temperature and volume concentration of nanoparticles on different thermophysical properties, to evaluate the effect of presence of nanofluid and the change in the temperature, the flow rate, and nanoparticles type concentration on the heat exchanger performance, to analyze the data for heat transfer and study heat transfer coefficient when nanofluid is employed. Now we will go to the result and discussion. The effect of nanofluid on density at certain temperature. As you see here, there are relation between the density and also the concentration of the nanofluid, different nanofluid, and also different temperature. We estimated of our nanofluid at different concentration and different temperature. Here we can see the density of our nanofluid varies concentration at 20, at temperature 20 Celsius. Also, we can see here the density of our nanofluid varies concentration at 60 Celsius. We can notice from these two graphs, the curve reveal the linear relation between the density and concentration. Also, we can see the density of nanofluid is reduced when the temperature increases. So at every volume concentration. We can move now to another point, the effect of temperature of density for different of nanofluid. Also, we can see here the relation for each nanofluid. We can see in the relation between the density and temperature. As a note, the density of nanofluid is reduced when the temperature increases at every volume concentration. We will move now to the next point. It will be about the effective of nanofluid in thermal conductivity at certain temperature. As you see here, we calculated the thermal conductivity of our nanofluid by using Maxwell model. The figure show close result for aluminum oxide and copper oxide, because the thermal conductivity value for aluminum oxide and copper oxide of nanoparticles are close. Also, the data were introduced for each volume concentration as a variation of temperature for these nanofluid. As you see here also, we note that the thermal conductivity of nanofluid is increased. The thermal conductivity of nanofluid is increased when the temperature increases, as I show in these all figures of different nanofluid. So at every volume concentration. Okay, so the effective of the now we'll move to the effect of volume concentration and temperature on dynamic viscosity of aluminum oxide. Also, we obtain the dynamic viscosity for each volume concentration and dynamic viscosity varies concentration at every temperature. We note here the volume the value of dynamic viscosity decrease when the temperature increase, while it increase by volume concentration. So there are questions why we already only use the aluminum oxide. The reason of our equation that only used the aluminum oxide because they only depend about the base fluid. So all previous nanofluid will have the same reason. That's our reason. The effective of nanofluid on specific heat at certain temperature. Also, we can see the effective of nanofluid specific heat of certain temperature. Here we can see the effective of our nanofluid at different concentration at temperature 20, firstly. Also, we can see the value of different concentration at temperature 50, as you see here in the value. We calculate the specific heat for our nanofluid at different temperature and different volume concentration. We plotted the specific heat, various concentration one time, 20 in the temperature 20, the other time in the temperature 50. So we can note that the linear relation between the specific heat and volume concentration are when the volume concentration increase, immediately the specific heat decrease. That's our result. Also, as you see here, according to these figures, we calculate according to these figures, the value of specific heat at different temperature in the range from 20 to 60 degree are close because the effective of volume concentration in specific heat are clear. Now we will move, sorry, to the heat transfer. Wait, sorry about that. Yeah, here. Heat transfer, yeah. Yeah, sorry about this missing technical. Now we will move to the heat transfer model. As you see here, a variation of volume rate, average heat transfer rate at different volume concentration for different nanofluid. We will move to this model in plate heat exchanger, and we started our result and discussion by showing variation of real number and the average transfer rate. As we see here in the figure, the aluminum oxide and copper and iron oxide and titanium dioxide, these figures show the close result for previous nanofluid because the result of value of specific heat is close. We note the average heat transfer rate value is increased when increasing of volume flow rate and volume concentration. As you see here also, we can see the variation of real number and Nusselt number at different volume concentration for different nanofluid. We can see the Nusselt number value and here transfer coefficient increase from these 8 figures. The first 4 figures and the second 4 figures. We can see the increase from the Nusselt number value and the heat transfer coefficient increase with the increasing of real number at nanoparticle. We note that the enhancement in value in Nusselt number and the heat transfer coefficient in nanofluid will compare with the base fluid. As you see here, in the variation of real number and convection, sorry about that, yeah, variation of real number and convection of heat transfer coefficient at 1.5% volume concentration for different nanofluid. As you see here, the convective of heated coefficient of copper, as you the red one, are greatest value. So the greatest value of that. So the greatest value in here it will be the heat coefficient of copper oxide. Okay, so after that we already make a compare between our theoretical result and experimental result, as you see here. When we already comparing our results for theoretical model that we already used in the experimental result and of other researcher with nanofluid that they investigate the following figures here and here. We are plotted our compare with NU of different loading of the nanofluid, as you see here, okay, with water data at different roll number with experimental data of Mr. M. Sarfaz, MW, CN at H2O, nanofluid. While the compare the H of different loading of nanofluid with the water data at different load number with experimental with P. Salah, as you see here in the next one. Of Ni, the Mr. B. Saleh, it will be the NiH2O. So the result of the theoretical model and experimental model agreed. While the NU, the first one, and H reached the maximum larger volume concentration and higher real number. As you see here, the highest line, all of them agreed the results. Now I talk about the conclusion. It notes that the density of water-based nanofluid is increased with increased nanoparticles. It's observed that the thermal conductivity of water-based nanofluid is increased. With the increase in the temperature. It's decreased. It decreased. Then is it detected that the increase of temperature leads to a decrease in the viscosity of water-based nanofluid. The specific heat capacity decreased when nanofluid volume concentration increased. The average heat transfer value increased with the increasing volume rate and volume concentration. With the increase of nanoparticles volume concentration and real number, the convection of heat transfer coefficient and this number are enhanced for following data. It's observed that the copper of nanofluid has the highest convective heat transfer coefficient. Thank you so much to your listening.